emailed it to you too. What was the homework I gave you for Monday?
Complex numbers.
Complex numbers do what? Review them, right?
Yeah.
All right, so somebody tell me what a complex number is. I equals. You're complex.
I equals
Square root of negative.
Square root of
-1.
square root of -1. And then anytime you end up with a negative under a radical, you use this idea to deal with the negative so that you can continue on. What does a complex solution look like on a graph? Doesn't it? Can you see complex solutions on graphs? Because like if I gave you this, you know, x squared plus 4 equals 0, and I said solve, does that have a real solution or a complex solution? Complex. Okay. So if this was like y equals x squared plus 4 and you graphed it, what does that look like on a graph, that parabola? Opening up above the intercept, or above the axis, right? So like this has no real solutions, but it does have complex solutions. So there's nothing that I see by looking at this that I see a complex solution, but you'd know it would have one, right? So you can solve this. So if I asked you to solve this, this would have been in algebra 2, you would have had x squared equals -4, and then what do I do? Square root both sides. So x equals plus or minus the square root of -4. And then, okay, so what is I? I is the square root of -1. So if you needed to, I don't require you guys to show me all of this, but just to remind you what it is, I could rewrite this as the square root of -1 times the square root of 4, right? You're allowed to put square roots together, multiply the things under it, or separate them. So then this becomes I. This becomes 2. So the answer would be plus or minus 2i. Okay, so when you guys learn this in algebra 2, it's separated. And you got the pieces of it, and you practice doing this. Now the assumption is that you guys know this, and you know how to do it. I asked you to look at those appendices in the back and review. So hopefully you did that. And if you didn't, go back and look at it and review it, especially if you're trying to answer these problems and you're getting weird results. Okay, so the first thing we're going to do, so this is all section 4.3, we're going to talk about the fundamental theorem of algebra. Sounds pretty important, right? If it is the fundamental theorem of algebra. You guys learned this in algebra 2. Anybody remember it? Anyone? No? Okay. Fundamental theorem of algebra is basically every complex polynomial function has at least one complex 0. Sounds exciting. So, the fundamental theorem of algebra says every complex polynomial function call it f of x. So every complex polynomial function f of x with a degree greater than or equal to 1 has at least one complex 0. That's the fundamental theorem of algebra. And then your book, this is the best line in the book. We shall not prove this result, as the proof is beyond the scope of this book. I just read that directly from your textbook. So, we don't need to prove it. It is not pre-calculus material to prove it. So, we can still use it. Okay? And we have this theorem, we have some other theorems, and if we put them all together, then we can just figure out how to use it on other problems. Now, I do want to point this out. They say complex polynomial function. That means the functions, the polynomial, can actually have like complex numbers as like the lead coefficients. and everything's super ugly. But then the book thankfully says, hey, for this class and for pre-calc, we're going to keep the coefficients real. So we're not going to get crazy into complex coefficients on all the pieces of your function. We're going to stick with real numbers. It does work all the way to having even all the coefficients be complex, but we won't do that for pre-calc. Okay, so we have the fundamental theorem of algebra. We keep real coefficients. This plus the factor theorem then tells us this, that every complex polynomial function can be factored into, I think they just say n linear factors. And not necessarily distinct. Necessarily. Why I can't spell all of a sudden. Necessarily distinct.
When you're a teacher.
You see the coping strategies, right? You have to be perfect at everything. You just have to know how to hide what you can't do. What does it mean if I say the factors aren't necessarily distinct? How can you have non-distinct factors? What does it mean if I say something is very distinct? Can be kind of straight to the point, or like, wow, she's a very distinct hairstyle. It's like very different. It's very clearly delineated from something else, very clearly separated. Like if I say you have 4 distinct zeros, they're 1, 2, 3, and 4. They're distinct. But you could have 4 zeros, and it could be 1, 1, 2, 2. So 2 zeros of 1, those aren't distinct zeros. It's the same number twice, right? So when they say not necessarily distinct, that's the case where you could have like a repeated 0. So you got to count it as if 2 is a 0 twice. Remember that's that touching, multiplicity, right? If it touches or goes through, you can have a multiplicity of 2, a multiplicity of 3. So those are zeros. They're separate zeros, but they're not distinct zeros. Which one is it? Let's remind ourselves. Multiplicity of 2, 4, 6, even multiplicity. What does it do on the graph? Touch, go away. Odd multiplicity, go through. Okay, good. So we can factor it into this form that will say f of x equals, and then we just write it in that factored form where we use r's for our factors. So they're saying that you can, because we know that every complex function has at least one complex 0, now we can say every complex function can be factored like this. Part of the trick in here is all this mumbo jumbo, and you're like, sometimes you get all this and then you don't actually use any of it, you just solve the problems. This is like the backstory. This is saying what we did with real numbers, we can do with complex numbers. The factor theorem says that real polynomials have factors. Now we're saying, well, we can do that with complex polynomials as well. And then we can find all these zeros. And then you guys learned something last year in Algebra 2, another fact about these kinds of zeros. It's called the conjugate pairs theorem. Does anybody remember that from Algebra 2? It was an extra rule that only applied when you looked at complex zeros. Anybody? Like, it would be like this. Like, if I told you that 3 plus I is a 0, can you give me another 0? 3 minus I. Do you guys remember that from Algebra 2? If 3 plus I is a 0, then 3 minus I is also a 0. If 4 minus I is a 0, then 4 plus I is also 0. Okay, so you are remembering this idea. It's called the conjugate pairs theorem. That these always come in conjugate pairs, so you always get the plus or minus of it. So that's something from Algebra 2. Let's write that down. So it's called the conjugate pairs theorem. kind of nice. It helps you figure out all of your zeros and helps you find the function easier. So the conjugate pair theorem says basically if R equals A plus BI is a solution, then R equals A minus BI is also a solution. So if you wanted to write that out as like a sentence, you would basically say all complex numbers appear in conjugate pairs. They're always the plus or minus. They always come together like that. All right, I've got one more thing to write in your notes from 4.3, and then the rest of the stuff we're doing today is how to use it. It'll be like examples, okay? The last piece, so we have the fundamental theorem of algebra. We have this, which is a theorem that doesn't have a name, that follows from it, saying that you know they have complex zeros, you know you can factor them, you know that if there's conjugate pairs, you can get the plus or minus. The last thing, I actually talked to you guys about this before, is a corollary that says if the polynomial function has odd degree, it's got at least one real zero. So the corollary here is if a polynomial function has an odd degree, it has at least one real zero, because we're talking about complex zeros mainly.
Is that like a certain theorem or just like
They call it a corollary. They just say corollary, which just means it directly follows from all the others. Yep. We talked about this before. Do you guys remember why? Why would something that has a degree 3 or a degree 5 guaranteed have at least one real zero? Finger talking. Every time anybody does that, I just think about Elisa Cheng, because that was like her thing, was to speak to me with her fingers. So what does an odd function look like? End behavior is negative to positive or positive to negative, always opposites, right? So if the end behavior has opposite extremes, then it's going to cross the axis at least once. So that's why you get the at least one real. Okay? So you're going to be doing problems where basically I give you some of the zeros or I give you a function and I say find it. You're going to try to put all these pieces together. So you have to remember that if you have a complex number, use its conjugate pair. They always come in pairs. If I tell you it's like a 3rd degree or 5th degree, you know that there's a real zero somewhere. Okay? And then you're basically going to try to build equations from it, or maybe we'll try to find the solutions from it. Okay, so this is all the theorem-based stuff. And so now what we're going to do is we're just going to do a bunch of examples so that you guys know what your homework's going to look like. Okay, so here is the first type of problem I'm going to have you do is basically I'm going to ask you guys, I'm going to give you information on a polynomial function and I'm going to ask you to find the remaining zeros. So I think I have 1, 2, 3, 4 types of examples I'm going to give you. So this is type 1. And basically the instructions are find the remaining zeros. Okay, so let's say I tell you that it's a 5th degree polynomial. And let's say I tell you that the zeros, I'm going to give you some zeros, I'm going to tell you it's 1i and 2i. We're starting easy. We're starting, it's like a softball pitch, right? This is an underhand serve for volleyball. To help volleyball people understand. Unless it's my underhand serve, then it's nice.
Or we should.
That's funny.
Because he's bad.
Mr. Mr. Chan underhand serves are the kind that go up and like almost touch the ceiling and then come down. Sometimes they go so high, you get like so distracted waiting for it, you end up missing it up, and then he thinks he's like really powerful. Mr. Chan, when he serves, he's like,
so
whoop! He makes that little sound. Every time he hits it, it goes super high, and so then you almost have like too much time, and you hit it wrong, and then he thinks he's got like
it's a real thing.
power.
In beach volleyball, it's a real thing.
That they'll serve super high.
They do like an underhand serve, but they do like flat-handed.
Uh-huh.
And they like,
Or they spin it.
they like do like
Yeah.
a ton of topspin, and they like launch it super high.
Yeah.
And it's really difficult.
It is.
God.
In tennis, you do that too. If you put a ton of spin on the ball, as soon as your opponent's racket touches the ball just freaks out. It goes weird. So you really have to like accommodate for it.
Yeah, it's like,
I kinda wanna
really
do that.
launch it.
That's
It's so
awesome.
good.
If you can master it, then probably
It's
Do it
so
volleyball.
I did it
Let's
once
see.
during practice. Yeah.
Okay.
We're better at beach because it's too
It's
Yes,
the
true. Not safe. All right. So how many solutions do we have?
for me, I think that was.
How many zeros should we have? It's fifth degree? 5.
No.
5? 5? Yes. Degree 5, 5 zeros?
What's
Okay.
the one where it's like n-1?
Turning
Turning
points. Good. Okay, so that's a good point. Whatever degree it has, that's the max number of zeros it can have. It's one less than that turning points, which makes sense. If it's 5 zeros, it can turn at most 4 times to make those 5 zeros. Okay, does it have a real 0? Yes, because it's odd. And I gave it to you once, right? But it crosses. So then all you gotta do is just use the conjugate pairs. So what are the 2 missing zeros? Negative I, negative 2I. Done. Problem over.
So you can't use it for real zero.
Right. The conjugate pairs is only for complex zeros.
He's laughing at me.
Pay her back later.
No,
Okay,
no phone
so
music for you.
at first that's all they're gonna ask you is to do that. So what if I said this? What if I gave you an example? That was degree 6. Do I have to have a real 0? That's degree 6? No. Okay. I could, but I don't have to.
Why do we want it?
Okay, and then if they give you these are the zeros. 2 plus I, negative 3 minus I, and 0. Find me the remaining zeros.
Okay, so 2 minus I and maybe 3 plus
Very easy, right?
I.
Real zeros, stand alone. This is
No,
just,
these are the really hard ones. Like, this is so hard.
so then we're also gonna have 2 minus I and then negative 3 plus I. Alright, so that's your warm up. That's your little brain massage, warm it up. Yes. Okay, now, next set of problems, they're going to give you something similar and they're going to ask you form a function. Now, it could be different. Don't get crazy and decide that you want to create a lead coefficient of like 347. Just don't. Let's just stick with lead coefficients of like 1s.
Aww.
Just make, unless you're really bored and you want to be crazy. But the next part, so the next set of examples is this. They are going to say, oh, that red sticks on the board.
Oh no. Uh-oh.
Okay, so this one is going to say form a function. Okay, so form a function with real coefficients using the information.
Oh.
So here we go. Ready? I'm going to tell you that the degree is 4. I'm going to tell you that the zeros are 3 plus 2I. And then also they're going to tell you this. They're going to tell you that 0 is 4 with a multiplicity of 2. So remind me what this means. If I tell you it's 4 with a multiplicity of 2, it touches but doesn't go through, and it's x minus 4 quantity squared. Good. Okay, so this is 2 zeros already, and this is 1 0. We need 4 zeros. What's the other one? 3 minus 2i. But now they're not saying just tell me the 0. They're saying make a function. So the format is, this is what I gave you guys earlier. It was this. F of x equals an x minus r1, x minus r2, dot, 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 all the way to x minus r sub n. I would encourage you, let's just go with 1 for a sub n. And then we're going to have to plug it in. Now this is where your algebra is going to bounce some of you. Slow down. Think carefully. Okay? So, we're going to form this function. Let's make a sub n be 1. So we're going to write these in. So I know that it's a 4 of multiplicity 2. So I could write x minus 4 squared, or I can write it as x minus 4 like that. It's up to you. Some people, when they write x minus 4 squared and they multiply it out, they forget the middle term. If you're one of those people, don't do that. Okay? How do I write this next one? X minus, okay. If I'm subtracting, do I have to put the 3 plus 2i in parentheses? Yes. X minus 3 plus 2i, do I have to do that?
I mean,
There's gonna be a statement.
you just like carry the sign.
Okay, what's the other one? X minus 3 minus 2i. If I didn't put the parentheses, would there be an issue? Yes.
Yes.
Joseph says no.
Oh wait. Oh yeah, because then it's like the same.
No?
Wait, no. Wait,
No,
yeah.
it wouldn't be the same. It's
No,
the
because
whole
one is
point of
negative
putting,
and one becomes positive.
yeah, the whole point of putting parentheses is to not have it be the same.
But then there's the same anyway.
No, are they the same anyway? Who's right?
Wait. I need to look carefully.
Look carefully. Think about distributing the minus sign. What happens? This one becomes x minus 3 minus 2i. This one becomes x minus 3 plus 2i. It's just coping in his own way. Okay. Okay, does it matter? Did I need this? Do I need the parentheses? Vince is so confident, he's just learning about numbers.
I think he's coping too.
And then you get all. Okay. Do I need the parentheses there? I mean, technically, should I put them there? Yes. Technically, once you distribute that minus across the parentheses, doesn't matter. I think that's what Yosef's saying, is that technically in the end, it doesn't change, right? Is that what you're saying? Like once you do minus 3, minus 2, and this would be minus 3 plus 2, it's kind of the same as not putting them there. I do think, though, if you're looking for someone to see that you have the appropriate skill, the knowledge of knowing those parentheses should go there first. That's probably a good idea. Okay. How do we write this? We're not done. That is not your allowed answer. So, ready for some ugly math?
No.
How about now?
How about no? I'm just kidding.
You could. It'd be less grading for me. I just didn't do it. Alright, so how do I get this? Oh no. Slowly and carefully. Okay, you need to multiply it all out. Go. Let's see how your algebra is.
It's gonna be amazing.
It's gonna be amazing. How does that even work? Okay, let me show you the way. Let me show you how the book suggests to do this, okay? Everybody take a look. Depends on your level of comfort with this. Alright, so we can write this out equals. I'm going to multiply this one out. That would be x squared minus 8x plus 16, right?
No.
Now, the book in their solutions rewrites this like this. They write x minus 3 minus 2i x minus 3 plus 2i. Why do you think they would take that intermediate step.
So you can.
It's like the complex.
Oh, and then you get the I squared and it becomes -1.
See how the middle terms disappear? Okay, so pay attention to this.
Slow.
Okay, if I gave you this, x minus 3 times x plus 3, what do you know about this?
X squared minus 9.
Yeah, middle terms disappear, right? So it's kind of nice. When you have exactly the same factors, but 1 plus, 1 minus, middle terms are gone.
And then it's.
Do you guys see that that is technically the exact same thing?
Sure. Yeah.
First term, second term, identical. Sign is different. So, make a little note for yourself. If you write it like this,
I don't remember like when we'll play it out. In the middle.
the middle
You get
term
it now, but then when you don't know later. So it's like.
will cancel. That makes it a lot easier for us to multiply and not have to multiply, and then later cancel, and you have more chance of screwing it up. So if you write it like that, you can get it to cancel. Okay? So, what can I write this as then? This would be x squared minus 8x plus 16. Okay, what's this other one turn into? Let's just do let's leave the x minus 3 in parentheses right now. Okay, so if you did this one, you would have said x squared minus 9, right? First term squared minus second term squared. Let's do the same thing here, but I'm not going to do too much in a step. First term squared, I'm going to do x minus 3 squared minus second term squared. What is 2i squared?
Okay, -4.
Yes.
So it's positive.
So you got to decide how much are you willing to skip here and risk screwing it up versus what are you going to write down. I personally, and especially if I'm turning this in for a grade or something, I would write it as 2i squared. 2i squared is 4i squared, right? I might write that first and then physically remind myself I squared is a -1, and -4, -1 would become a +4, right? I would probably not do all that in one step. Is our video okay? Is it still? I think they said it's like 30 minutes. Joseph, you can tell us if the video shuts off, right?
Yeah.
Okay.
Can you?
Okay.
Can you just do it?
Okay, so we keep going on this. So let's do a little bit of work here now. So this would become x squared minus, there is a middle term on this one, right? Plus 9. And then this becomes plus 4. Because it would be a -4 times a -1. Right? So that becomes plus 4. You guys have to decide your level of comfort in shortcutting some of this stuff. Okay, last step is just massive distribution.
That's just fun.
Yay! All right, keep going. We'll see if we all get to the same place once you've written it all out. $80,104.
Bless you.
160 plus 48, 208? Yes? No? Okay. So then that would be x to the 4th. Oh, I've got an issue here. I wrote square instead of cube. That would mess me up. That's a cube. This one is a cube. So minus 14x cubed. 58 by 61. 71. my confidence level on getting all that right is fairly low right now.
I got that.
Minus 14x cubed plus 77. Got it.
Yeah.
Celebration moment every time you don't mess up a coefficient somewhere. Yes. I did it again. Each time I thought cubed in my brain, I wrote squared. That's really weird. That's what you guys are here for, point out my errors. Griffin errors? No.
Oh my gosh. It's okay.
I kicked it by accident.
It's okay.
Nice.
What am I doing?
I saw a class or a t-shirt for sale that said English is important, but math is important. It's good, right? Kind of fits with your shirt.
How does it fit?
I know, right?
Okay, so the instructions here are form a function from the given. The first two problems I gave you, they were softballs, right? This is a little bit more serious. Maybe fast pitch softball stuff. Alright, so.
Are we going to MLB?
Okay, so I'm going to give you one more to try like this. And then I'm going to have you check it with each other. And see how you do. Okay, so here's the other one I want you to do. I want you to do degree is 5. Okay, so I'm going to have you do another one. We need to save this video and give it to Edward too, right?
Oh yeah, that's a good idea.
You guys can just start skipping class and we'll just videotape
Wait,
it and
what's
send it
the
to you
That's like,
later.
isn't that like
That was for
college?
Edward.
No, what is it?
Okay, so we're going to say degree is 5.
Edward and I took turns doing so.
The zeros are 2, negative I, and 1 plus I. Okay, no multiplicity. Okay, go. So, you guys are all going to work on this for a while. Let's pause. Joseph, can you pause the video while everybody works? And then we'll just start it again.